Hello everyone, my name is Lindbeck and my research has been on marine hydrokinetic turbine fault detection using signal processing. When you look at the marine energy industry, the biggest obstacles are economic and not technological. The highest costs after initial installation are associated with operations and maintenance, especially repairs. Some of the most common faults in a turbine are associated with rotor blades, those being something getting stuck to or growing on one of the blades, called a mass imbalance fault, or one of the blades getting skewed out of its normal alignment so that the edge faces into the current flow and the flat is facing resistance as it rotates. And that is called a hydrodynamic asymmetry fault. In either of these cases, you get an unbalance, and it causes a lot of wobbling. If that happens to your turbine, something is going to break. So ideally, we can detect this as it is starting or even before it begins and shut down the turbine and replace whatever has broken. The nice thing about this wobbling is that it's predictable. It creates a frequency at the same frequency as the turbine's rotation, since an unbalanced force is going around once per cycle. So when we look at three-phase power output, we see an extra sinusoid with the same frequency as the turbine added to our normal output data, which is usually pretty noisy. The problem with detecting this signal is twofold. First of all, it is a really small amplitude compared to the noise. It's almost impossible to see. Second, most of the signal processing tools that we have to analyze a signal like this, such as the Fourier transform, rely on the assumption that the frequency is constant over the entire time span. And since the current will speed up and slow down, so will the turbine, and then the frequency changes. But of the analysis tools that we do have, which can account for changing frequencies, we found the most success with the HILBERT-HUANG transform on our data, which looks like this. When you look at the HILBERT-HUANG transform, for example, on this kind of signal, which you can see is a sum of sinusoids, you may not be able to tell how many there are, what their amplitudes are, what their frequencies are, but once you apply the transformation, you get a Hilbert spectrum, which plots the different components in terms of frequency over time, with amplitude represented by their color. So in this case, we can see that there's a high amplitude at 5 Hertz, a medium amplitude at 1 Hertz, and a low amplitude at 20 Hertz. If we do the same thing to our real data, we can check the components that are following about the same frequency as our turbine, and then see if there's an abnormally high amplitude indicating an extra signal there. There are a bunch of different variations on this algorithm and parameters to mess with, and with the best version that we have so far, we've gotten data like this. So the data you see is essentially the average normalized amplitude in range of the fault frequency. And you can see with the 95% confidence intervals, we can distinguish between the baseline case and a 15 or 20 degree change in the angle of the blade. If we take the average over 100 seconds instead of 30 seconds, we get clear distinctions as the confidence intervals shrink, and we can now tell the difference in the 10 degree case. We've pretty much given up on 5 degrees. In future, one nice thing is that we can expand this to take into account different faults that create changes in specific frequencies. So obviously we could go to the mass imbalance faults I talked earlier, which produce the same behavior, but there are also other types of faults that will generate specific frequencies, such as bearing faults, which are currently the bane of existence for wind turbines, and gearbox faults, where one of the teeth wears out or breaks off. Hopefully, with these improved detection methods and preventative measures, we can save the turbine operators a lot of time and money and make in-current turbines more mainstream. Thank you.